Good morning, everybody. I trust you can hear me.
Yes.
Yes, okay, good. Thank you for the confirmation. Welcome to this one of the parallel sessions on the adaptation modeling expert meeting, I would say, workshop on climate adaptation modeling. This morning we have parallel sessions, and this is the session on adaptation policy and planning. As you know, the session is separated in two blocks of 1 hour each. I'm moderating the first one, and my colleague Jeroen Aerts will moderate the second block. My name is Bart van den Hurk. I'm residing in the Netherlands at Deltares, which is a water research institute. And as Deltares, we are involved in a project aiming to make an inventory of available adaptation modeling concepts and tools, and to give an assessment of these. And this conference is organized partly as a spin-off of that inventory activity. We have a small group. I've spotted most of the speakers that are lined up for the first hour's session are in the group. So Carlo Giupponi is here. Marc Zebisch is one of the attendants. Margarita Ruiz-Ramos has been spotted, and I'm looking for Reimund Schwarze, who is not yet in the attendant list. But as we are still very early in the session, I trust that he will come in at a later stage. We have a bit more than an hour. We need to finalize this session at 11:05, I believe. I'm moderating. I don't operate the platform. I do trust that the host is in charge of switching screens and moderating the microphone, the muting policies. We'll run this in a very straightforward manner. I would propose we have 4 presentations. The presenters have been instructed to take into account some time for discussion and questioning. So I will give a flag warning at about a 12-minute duration of the presentation, after which we can switch to a discussion, and we'll do that primarily per presentation. So we will not stack up all the questions until the end, but we'll have direct interaction with the presenters. I do not recommend to have interventions, oral interventions during the presentations, but I do definitely encourage you to use the chat function. If you do have questions during the presentation, you can post them there. I'll try to keep an eye on the chat, and we'll pick out a couple of these questions to the presenters. But if that chat function is running out very well abundantly, then it may be that not all questions will be answered in this discussion. And then I'll politely ask the presenters to take note of these and come back to the questioner after the conference. Yeah, I don't have any further announcements to make. The topic of today, climate adaptation policy. We have 4 different speakers that have made an analysis of policy and the tooling that is behind there. My background is basically mainly in physical climate modeling, so I'm not an expert in this adaptation policy domain by training, but I've been involved in various research projects and interactions with policymakers and practitioners to have some understanding of the required, say, information on climate change and climate impacts for policymaking. But excuse me if my interventions or questions are not very, expressing a very thorough understanding of the material, but I have a very thorough interest in the material. So with that conclusion, I would invite actually one of the co-organizers of this conference, Carlo Giupponi, whether he is ready to give his presentation. He's from the University of Venice and will talk about operationalizing climate proofing in decision policy making. are you ready to present your presentation?
Yes, here I am.
Okay.
Try to share my screen then and see if it works. Can you see it?
Yes, it's
okay. Wonderful.
Well. Yeah, thank you. Please go ahead.
Okay, so good morning, everybody. I'm Carlo Giupponi. As you said, I work at Foscari University of Venice and Dean of the Venice International University. I've been working quite a bit on climate issues, climate change issues, and climate change adaptation in particular. And that is the reason why we have developed some approaches to try to make what we know about climate adaptation, and in particular to make what we can get from models useful and usable for the support of policy and decision making. So what I'm going to present today is exactly about this, an effort to operationalize, as you can see, what we call climate proofing, so making our decision climate proofed, and but here, of course, decisions that are aimed at improving our adaptation to climate change and our resilience to climate change. So as usual, when we want to propose a method, what we want to do is, first of all, to refer to the most important policy and regulatory references, and in this case, the European guidelines for climate change adaptation strategies, which we know are under revision currently. What I want to drive your attention to with this slide is that more or less, this is, I would say, simply a generic decision support or decision-making cycle, because the main steps, apart from the fact that we can read adaptation in a couple of steps, these are really the classical steps that we can find in any kind of decision-making cycle, adaptive maybe, but this is therefore what I want to say is that this is rather generic, and we need to make it more operational. And today we focus in particular on the role of models. So if we want to take a classical approach to climate change adaptation, making use of models, we know very well that integrated models, or let's say, hopefully, maybe as an ambition, a single integrated model or combined models are quite important, and in my opinion are the only tools we have to really try to explore ex ante what could be the effect of the adaptation options that we want to assess and that we want maybe to implement later. So these three steps are a linear sequence that can become, as we have seen, a circular process, a cyclic process. And what can be seen here is simply obvious. We need to have a notion about past climate, but we need also to have capabilities to explore future scenarios. In this way, we can really assess adaptation options, and by means of integrating models, we can support the identification of preferable solutions. But what we want to stress here is that this is unfortunately not enough to have an operational and effective support of decision making. What we should have instead is a more articulated sequence of steps, in which you find the same of the previous slide, but also some new ones. In particular, we want to stress the need to have the development of a conceptual model, which should be a shared conceptual model at the very beginning of this process. And this conceptual model must be developed with the involvement of stakeholders. And this is therefore a very important step that we include in our flow chart. Then another point that I would like to stress, and this could be an interesting issue to be discussed, is that at least in our opinion, we never find a mechanistic solution in terms of modeling to simulate all the components of the systems that we want to simulate, all the components of the knowledge we need. And therefore, we typically need the involvement of experts, and we need to have some sort of elicitation of expert knowledge to be combined with what we can do with simulation modeling. Plus, we need to process the outcomes of these two main sources of information, integrated models and expert knowledge. And our suggested solution is multi-criteria analysis. We know very well that we can use also other methods like cost-benefit analysis. But in our experience, at least, we found the multi-criteria analysis as a much more effective approach, if not for other reasons, because it is much more intuitive and much closer to the conceptual approach that we usually find in our decision makers. But what is again peculiar of this context is uncertainty. Adaptation is intrinsically affected by uncertainty of different and many sources. So these are the elements of the decision-making flow chart that we have to approach and for which we have to find operational solutions. So we have only 12 minutes and we need we have to try to be as concrete as possible. So I move immediately to try to explain what I meant by showing a case study which was in the field of critical infrastructure, in particular airport development. Climate proofing in this case meant the analysis of how the classical approach for designing new infrastructure should evolve in order to take into consideration climate change, and in this case in particular the risk of floods of the runways of this airport. So once more we need some reference conceptual model, and we prefer to approach this taken from the IPCC SREX report of 2012, in which I'm sure it's very familiar to all of you, but just to point out that the main elements of these conceptual model are in fact risk at the very center of the thing, made by the combination of vulnerability, exposure, and hazard, so the weather and climate events that can generate some hazard. So having this as a reference, let's say, what we wanted to do is to develop this conceptual model into something much more detailed and tailored to the case study. So here you can find more or less the same elements: hazard, vulnerability, exposure, and risk. But of course, you find all the elements that characterize the system that we wanted to analyze, that we had to analyze. And here you find, for example, the need for water pumps, for drains, in order to cope with the vulnerability of the drainage system. We have the elements that are exposed of the system, the physical elements: roads, bridges, junctions, parking lots, and runways that are then exposed to risk. And so these are all the elements of the systems that are dynamically connected that we wanted to include in our system analysis. In order to do that, as I said, our preference is to adopt a multi-criteria analysis approach. And here you find 5 groups of criteria that we have identified as being the most important for the decision. And here, once more, I stress your attention to the fact that only 2 of these groups of criteria can be assessed with quantitative approaches, at least in our case, but maybe also in general. Economic analysis can be carried out with quantitative approaches. In this case, the hydrology, hydraulic modeling, and climatic modeling could be, in fact, approached as usual with quantitative modeling. But for example, the managerial system, the identification of various dimensions of the resilience and collateral effects could only be assessed through expert elicitation by the involvement of local experts, and therefore the conversion of their expertise into some sort of criteria characterizing a set of alternative options for the management of this new infrastructure. So what we did in the past is to develop a decision support system that we, through a long series of European projects, and that we kept somehow alive over time. And here we formalized the problem. We ran a classical multi-criteria analysis with the analysis matrix, evaluation matrix, identification of weights. And the classical result here is a deterministic ranking of the option. But as I said, what we wanted to do is to go beyond this to include the consideration of uncertainty, which is very, very important in a climate change adaptation context. So, for example, here, you can see in the graph and in the table below, the variability of the weights expressed by our experts. There are some criteria that have found a very ample spread of weights because the consideration, for example, of the top management of this company as compared to the technical staff were in fact different, and the emphasis they put on the various dimensions of the problems are indeed different. And this is an important source of subjectivity and uncertainty that we have to consider. So in practice, what we did in our analysis was to carry out a very high number of analysis, parallel multi-criteria analysis, taking into consideration the diversity of opinions of experts for the qualitative criteria, the uncertainty of the quantitative criteria coming from models, and the different risk attitudes that we could consider with the specific order-weighted averages approach that we adopted. So in total, we simulated or we ran the assessment more than 10,000 times. And therefore, we needed some tool to explore and to dig into this huge set of possible analysis of the problems. We use.
Carlo, sorry, you're at 12 minutes now. So
okay.
Yeah, thank you.
We have used CART and as a data mining technique to extract from this huge data set the results. In order to communicate the results, we typically used this kind of histograms, for example, showing that option A1 was the preferable one. And in particular, through the use of CART, we could also show these charts, for example, allowing our decision makers to identify all the critical values of the criteria that could drive the decision to different alternatives and reverse the ranking order. So I will skip this and simply move to some conclusions. First of all, we want to stress that decision making for climate change adaptation is affected by what we call deep uncertainty. The climate change drivers must be considered jointly with others, and in particular socioeconomic drivers. And for this meeting, modeling outputs cannot be immediately used by decision and policymaker because they must be coupled with other sources of knowledge, local, collective, subjective, qualitative, within an integrated platform for decision support. And therefore, a combination of qualitative and quantitative assessment with multi-criteria analysis and data mining technique, we think can significantly improve the effectiveness of our approaches and the potential of modeling techniques alone. And eventually, we can say that what we have to do, in our opinion, is to move from traditional assessment based on deterministic and probabilistic search for optimality towards robustness. And with this, I thank you for your attention.
Yeah, thank you very much, Carlo. This is really very timely, this multi-criteria, multi-dimensional approaches. We have time for one question from the audience. And if there's no one, I could ask one. You could raise your hand in the chat in the participant panel. There is a raise hand button. But okay, if not, the one question I have still, in some way, this quantitative and qualitative information has to be combined in order to make these, you know, weights. Sure. How do you do that with these qualitative measures? What you have some unit of that for which you can combine all the elements. How do you do this?
Yes, I was running a little bit too fast when I was explaining this. We typically use questionnaires, of course, and we try to somehow convert a qualitative knowledge into some sort of quasi-quantitative information, for example, by using Likert scales. So we ask our stakeholders or experts to specify for each of the options what they expect, for example, in terms of a given criterion, in terms of comparative performances they expect. Of course, this is purely qualitative at the origin. It is subjective. But our opinion is that we have to find solution to deal with this subjectivity,
exactly,
and to, with this uncertainty, and not try to avoid it.
Yes. Oh, excellent. Thank you very much. Yeah.
You're welcome.
Thank you for the clear presentation. We can move on to the next one. Marc Zebisch, are you ready to pitch your presentation? And you're going to talk about a long impact assessment chain, I understand.
Yeah, actually, I think what I'm going to present is very, very similar,
okay.
luckily. So maybe it's a good transition. Do you see my screen?
Yes, we can. Please go ahead.
Perfect.
Yeah. I'll give you a 12-minute quick warning, okay?
Okay, thanks. Yeah, so basically, I want to present a concept which we have developed here over the years, which is called climate impact chain. And it's really very similar to what Carlo presented. So basically, it's a conceptual model, and it has been applied already more than 20 times now, mainly on the national scale. So we started in Germany, so we did the second and the third climate risk assessment for Germany, but we also developed guidelines for GIZ, the German Development Corporation, and they have then applied these in Bangladesh, in Madagascar, Burundi, and so on, so mainly in the development context. And the main ideas, I can maybe already skip to that one, is exactly the same which Carlo presented. So basically to model and operationalize the IPCC AR5, AR6 risk concept, which basically says that risk is the result of vulnerability, exposure, and hazard. So hazard is just one component, and we often see that while we have some model results and data on the hazard, particular climate hazards, often the vulnerability and exposure components are underestimated. They are not so data rich, and mainly if you look to the future, we have hardly any scenarios on vulnerability or exposure. So that's important, like how the population, for example, develops in a country, or how the income structure will change. So I give you a short example how we operationalize that. So this is a kind of fictive example. So it's a catchment where here's the sea, here are the mountains. You see some forest on the left-hand side. And here we deal with the risk of floods, but not of floods as such, but of the damage of property and loss of lives due to flooding. And of course, we know that there is a hazard component, so it's mainly heavy precipitation, but there are other factors like deforestation, wetland degradation, or population density, which are part of that. And then, very similar to what Carlo presented, we simply conceptualize that in chains. So we always start with the risk at the bottom, then we ask ourselves, okay, what is the hazard which is triggering this risk? And then you see already that the vulnerability box is much bigger than the hazard box. We have a bunch of vulnerability factors, and they might be related to the environment. Like, for example, a reduced natural retention capacity or deforestation, but We also include exposure factors, like, for example, the population density or the density of buildings. But then there are also more socioeconomic factors, like, for example, a lack of urban planning, which leads to the absence of flood-resistant housing. And this is already super simplified. So in reality, our boxes are maybe 3 times more. It's just that we can't squeeze that in a PowerPoint. It's just to make you aware or make you understand how this concept works. So it's a conceptual model, basically a paper model, identifying factors which leads to the risk and classifying these factors into the risk components, hazard, vulnerability, exposure. And that's exactly, so I made a screenshot of Carlo's presentation. So that's exactly what Carlo presented just 10 minutes ago. So this conceptual model and also the requirement to include expert knowledge. So that's exactly what we do, because how we build these impact chains is usually very participatory. So we really go into the countries, into the region, we use maps, we let the people explain where is the problem, what causes this problem. Then we are identifying factors, we are prioritizing factors, and then slowly in workshops, we build these impact chains as real paper models. So in the beginning, they are really paper models. This is, for example, in Azerbaijan. So this is why you might not be able to read this language here. And here it's on drought risk and landslide risk. And from these paper models, so then we go basically back to the expert mode. So we clean up all these models. We try to evaluate if the hypothesis or the ideas of the stakeholders in the field have been correct, and use these impact chains as a framework or as a backbone, if you want, so for an assessment. And one option to do such an assessment, and I think again it's similar to Carlo, is an indicator-based assessment. So that means we try to identify factors for which we can find indicator, and maybe most important is we don't let ourselves drive by data availability. So we let ourselves drive by the importance of factors. So that means if this lack of urban planning was identified as super important, we don't leave it out just because we have no data. And this is exactly where this expert assessment steps in, and it supports what Carlo was saying, that just a model or data-driven approach is often not enough, because you simply have to neglect factors which might be even more important than the one for which you have data. So that's maybe the main message here. And then it's exactly the same mixture of quantitative and qualitative information. So for some information, usually the hazard part, we have data. For others, we have to ask experts, and we do that also in a semi-quantitative way. So using evaluation schemes, for example, from 0 to 1, or using 5 scales. And then for the ones where we are not so sure, we really let the stakeholders vote, basically. For the ones where we have data, this is the example of Burundi. Of course, you can use fully integrated models. So this is, for example, an erosion model which was driven by climate change scenarios. It's really this mix of where you have data on models, impact models, use them. Factors which are important where you have no models. Use expert-based knowledge, do a qualitative or semi-quantitative assessment. And usually this is the scheme which we use to combine then all these elements. So we put them all in a common assessment scheme, which is ranking from optimal to critical. And there's also a weighting process like Carlo presented it. And then basically we can combine these several layers, can aggregate it to several scales, and can, for example, create maps for hazard, exposure, and vulnerability. You can even merge that to overall risk maps. But there we always have to say, so these risk maps are maybe the most condensed version, but also the least informative. So they might be useful for kind of identifying hotspots like this district here, which has the highest risk. But immediately the next step would be to understand why is the risk highest here. Because if you're talking about adaptation, but then I could basically click on that and understand which factors lead to the high risk here. And I see that here it's population density, of course, it's most exposed, and you have all these lack of policies for flood safe buildings. So that's basically to scale up or aggregate to the risk level, and then go down, decompose it again to try to understand what's the problem, which is then of course important for adaptation planning. So until now we are just only talking about risk assessment, not about adaptation planning. Yeah, the results are usually reports which integrate all these elements, so data, for example, this is an example we did for the UN for Azerbaijan climate risk assessment. So data like climate scenarios, the impact chains, but then also an overall evaluation of risk. So for example, here it's the risk of droughts, and we compare two different districts here. We give an overall estimate about the risk. So here it's moderate, even if the hazard is high, because for example, in this district, vulnerability and exposure are just moderate, while in the second district, we have the same hazard, but vulnerability and exposure are high. That's why we come up with a high risk assessment. But we also put a flashlight on critical settings and hotspots. For example, particular under risk are here small farmholders with rain-fed or poorly irrigated fields, inefficient irrigation systems, or agriculture on already degraded soil. So that really helps then to see where is the most, the highest demand for invention, basically, or you could call that also adaptation. And that brings me to the last slide. I mean, here we are talking about adaptation modeling, which was a new term for me, I have to say, and I'm still curious to learn what adaptation modeling exactly means. This is basically also what Carlo showed, where a risk assessment stands in the adaptation cycle, so that risk assessment is already used to identify vulnerabilities, then to basically help to identify adaptation options, but I think it's also important for monitoring adaptation, because that's a constant process. I mean, the assumption is that your adaptation reduces the risk, but a constant risk assessment could also be used to check if this hypothesis was true. So if after 5 years of adaptation, we really have a lower risk or still the same. And that brings me to my second last slide, which is showing that so in this process of building these impact chains, already on a participatory level on a workshop, we can already start to talk about adaptation options, or we do that. For example, if we identify that wetland degradation is one of the elements which lead to a risk of flooding or of damage due to flooding, we can immediately understand that wetland restoration would be a good adaptation option to reduce these vulnerability factor. Or if deforestation plays a role, then reforestation would be, of course, good. But also here for this absence of flood resilient houses, either technical measures like build elevated houses, or we could even say improve or introduce urban planning. So this would then be more a capacity measure. So that means these impact chains, usually we develop them for risk assessment, but we are using them already to identify adaptation options already on this participatory level. Yeah, and that brings me to my conclusion. So, I mean, we really made positive experiences with this concept, mainly because it's really something which is easy and comprehensive to understand. You're building it together in a participatory manner, and after your words, you have an agreed understanding of your risk in your specific context, in line with the IPCC AR5 concept. So we are not just applying a standard approach saying this is your risk, but we're, let's say, together with national, local stakeholders, elaborating the factors. Afterwards, the risk assessment or the elements are still in line with the IPCC AR5 concept, and as I was showing, they can at least support adaptation planning from the first phase onwards already on this level of paper models. But of course, there's some challenges, and I think again some have been already addressed by Carlo, and that's I think a very nice complementation. So it's on validation. So of course, we have here a hybrid hypothesis-driven approach, which cannot fully be validated. So I think we should find ways how to validate that, and this includes, of course, all these uncertainty analysis, which Carlo was mentioning. Yeah, one challenge is maybe since, I mean, we are talking always also at this conference here between mainstreaming adaptation planning, merging the disaster risk concepts with the climate change adaptation concepts. But in reality, the disaster risk concepts are still different. I mean, they are mainly using probabilistic assessments. They have these loss and damage estimation perspective, and particularly this probabilistic assessment is simply getting difficult with climate change, if not impossible. And I think there is a huge room for improvement, how to bring these words closer together and not just to try to adopt the disaster risk concepts for CAA and vice versa, but we must find also here some, let's say, hybrid solution, I guess. and maybe most important from my point of view, if we speak about risk and risk assessment, is that risk is not something objective. So it's a value-based approach. So that means in the end, we always have to start with the question, so which objectives do you want to protect, or what do you want to avoid? So there might be even an acceptable risk, for example, for Germany, to give you that example. We have to decide, do we need to have agriculture which is really fully supplying Germany, or is that not so important because we can import things? So if a risk is high or low really depends also what objectives you have or what you want to avoid. Okay, so with that, I finish here, hopefully in time.
Thank you, Marc. Now, you were repeatedly referring to Carlo's presentation, saying that you duplicate, but I think you really enriched the presentation of Carlo a lot with this. And you have the prize for the best adaptation, that you immediately adopt a screenshot of the previous talk and yours. That is I've never seen that happen before. That's very good. Thank you. I see two hands raised. We have a bit short of time, so let's quickly pick it up. Rob Wilby. I cannot unmute you, so yeah.
Okay, yeah, thank you, Marc. That was a really great presentation. My question is about the participatory approach. How do you ensure fair representation of all views, diverse views, and diverse positions and constituencies? Because in participatory approaches, as I'm sure you appreciate, there's often a danger that the most vocal, the most powerful are best represented, and it's their ideas that go all the way through your decision chain to the end of the process. So how do you get fair representation of the full suite of views?
Oh, that's right. I mean, usually what we, thanks for the question, Roger. So usually what we do, we have usually at least 2 workshops. So if we are now talking about, for example, Azerbaijan, the first one is more with, let's say, official representatives and national experts, so like from the weather service, from the environmental agency, more, let's say, more the official point of view, which is often very useful, particular also for the data perspective, because these stakeholders do not only have an opinion or expertise, but they're often even data providers. And then we have a second workshop, which is more with local stakeholders. And there you usually get a completely different perspective and completely different reasons. And it's often, let's say, for us, often these local stakeholder workshops are often eye-openers, because you learn some complex relationships which you would not have considered. Just to give you a super short example from Tajikistan recently. So there we were also trying to understand land erosion related problems, and it became clear that the biggest problem has to do with the post-Soviet way of pasturing, so the over-pasturing, which was not considered by any of these high experts' opinion. Yeah, so that's the way how we do it. So 2 separate workshops, one with, let's say, official, more authority-based experts, and then one with local stakeholders. And there we also are always taking care about the gender dimension. So if we try to have as much women as possible, and usually we have even female local partners, which are then even grouping out with the women and are just talking to the women, which is sometimes even another interesting, different perspective.
Yeah, thank you very much. I think that really makes sense. Sorry, Jeroen, can you put your question in the chat? Because for the sake of time, I really would like to move forward to Margarita's presentation. Sorry for that. And note that also, yeah, Margarita put a question actually still to Carlo. And so maybe you could pick that one up in the chat as well. So Margarita is bringing us to uncertainty reduction or assessment, at least mapping. Please go ahead. And thank you, Marc, for your nice presentation and responses.
So I'm going to present today a work done with my colleague, Alfredo Rodriguez. And thank you for inviting us to this interesting event and session. And well, in the last report of the World Economic Forum, failure in addressing climate change and related issues are identified as the risk with higher probability and impact. So the need for adaptation is clear, but the main barrier for it is the uncertainty that my colleagues already mentioned. the uncertainty that accumulates through all the assessment process and then prevents the users to consider our results, the research results, useful for solving the problems. So today I will present our approach to handle this issue. So we will be using observational meteorological data, both from stations and aggregated data sets, and an ensemble of regional climate model outputs for climate change projections, and crop data and crop models, the widely used crop data from experiments to calibrate the models. And as this uncertainty make us walk a tightrope, that is lazy, it demands from us to be smarter and come up with strategies to manage it. And so I'm going to talk about some of them, mainly about ensemble modeling, about methods to increase the confidence of the results we produce, to explore different futures, the response surfaces to assure economic viability. So let's begin with the response surfaces. These surfaces are plots to assess the response of an impact variable. In this example, is going to be crop yield, to systematic perturbation of changes of two explanatory variables, typically precipitation and temperature. And you will see nice examples in a presentation after the coffee break in this session by Carter and Fonseca. And when these plots are showing the difference between impact simulated with and without adaptation, then we can call it adaptation response surfaces and are showing the adaptation response to specific changes, combined changes in precipitation and temperature. So for a particular combination of precipitation and temperature change, we can see what is behind the final data using this plot. Consider here that we are using an ensemble of crop models, of 11 crop models. And in the horizontal X, you are looking at the possible ensemble size that we could have used to construct the ensemble from the whole set we have. The vertical X is showing the adaptation response simulated for each one of the members of the ensembles after averaging the simulation period. So this is to say we are looking at the percentage of yield gained or loss when adaptation is applied. So ensemble size 11 corresponds to the average results using, in this case, is the median, while individual models are shown for ensemble size equal to 1. So if we would have used a lower sample size, we could have composed it by using different members combination. And after averaging them, we would have obtained different final results. This is represented by each gray circle. So each gray circle comes from a different potential ensemble. So we wonder if the results would have been the same for these different possible ensembles when we change ensemble composition and size. So we have developed this ensemble outcome agreement index to answer this question and to test the hypothesis, for instance, that adaptation response is positive and measure how confident we can be in this hypothesis to be true based on the agreement between ensemble members. So this index ranges between 0 and 1, being 1 the maximum confidence level, but already 0.8 is very high confidence already. So the details are in the paper quoted there, but a key variable of this index is the minimum ensemble size from which every combination of models of ensemble members fulfills the hypothesis and by comparison with the maximum ensemble size. So let's see this with a study case. This is an adaptation study of winter wheat, for which we can see the ensemble outcome agreement value, index value, for a set of adaptation options. And columns are showing the results for different adaptation options, shorter, standard, and longer cultivars, and within each one for early and standard sowing dates. And files, or rows, show results for winter and spring wheat, and within each one rain-fed and supplementary irrigation consisting on one single event of 40 millimeters of irrigation at flowering. Each subplot shows the result, the responses the results of the index for perturb different combinations of precipitation and temperature changes and increase CO2. So in these plots, the green dots, green and blue dots, are results for which the ensemble outcome agreement is very high or maximum, while gray areas show options that were recommended before the application of this analysis, this index. So in these plots, we can identify already some rainfed options that are valid, but many options for spring wheat, many options with when introducing supplementary material, supplementary irrigation, and importantly, many options that cover all the precipitation and temperature combined changes that among those that are projected. So in spite of the uncertainty of P and T projections, or no matter how it's going to be the evolution of mean P and T, we still have some valid options. So it's a way to manage this uncertainty. And not less important, in the red rectangle, you can see options that were previously recommended that do not provide good confidence, actually. So although crop, model, and sample size and composition do affect final recommendations, it's possible applying this kind of techniques, come up with adaptations with high confidence. Another study case is the analysis of the fruit tree phenology for adaptation. And here we use chilling accumulation models combined with a measure of economic viability, the safe winter chill index, and also our ensemble outcome agreement index. And we calculated the chilling accumulation period and total accumulation value for an ensemble of regional climate models for the outputs of the models, and compare them with the chill requirements of the main commercial varieties of olive, vineyard, peach, plum, apple, cherry, and almond in Spain. So in the plot, you can, sorry, this is here, yeah. Sorry, I missed the right slide. Yes, so in this plot, you can see all the calculation behind a single cell with average value from different model projections and years. So each cell has a lot of modeling work behind. But in these maps, I'm showing the regions of Spain for which the confidence in fulfilling chilling requirements is high, as measured by our ensemble outcome agreement index, for 3 periods in columns and 2 RCPs in row for a chilling accumulation model, the dynamic model, and for 3 thresholds of chilling requirements, the low, medium, and high, that represent 3 types of varieties. So high, for instance, the color blue would be the varieties with higher chilling requirements. So now we can match varieties and suitable areas with high confidence supported by this index. And also is possible to obtain the confidence level measured by the index of having safe winter chill for a specific case that is shown here for Seville, that is the location in Spain with the largest currently production of almond. And with bars showing and colors showing the confidence levels, and for different varieties that are shown in the horizontal X for 2 periods and RCP2. So in spite that the safe winter chill areas will be reduced, we have options to move crops to close areas, and also to selecting carefully the varieties, matching varieties. So this makes adaptation possible with high confidence as measured by our index. And this is the kind of information that can be easily used by farmers and technicians, and combined with these decision support tools that have been shown and that can be used as inputs in this multi-criteria framework that my colleagues have shown before. So In conclusion, some uncertainty of the adaptation of recommendations can be handled by making a better use of the available information that could include combining some pre and post simulation, post methods, previous and post adaptation simulation to generate high usefulness information for decision making. And also very important to avoid maladaptation. So biophysical and economical adaptation is challenging, but at least in our study cases, it's possible, and it's possible with high confidence. And still, climate change mitigation matters for adaptation because you saw that the results are not the same for the different RCPs. So our research now is focused in progressing in reducing uncertainty, extending the research to more crops, location, and commercial varieties, as has been asked by, for instance, some farmers association in Spain that saw our results in some workshops and demanded us to collaborate with them. And then now we are moving from this approach of driven by data availability that Marc mentioned to more focus on users' requirements and needs. So we are now moving to commercial varieties and locations that they are asking for to increase applicability. So thank you very much. That would be all.
Thank you, Margarita. Nicely in time. Is there any question from the audience? Please raise your hand in the participant panel. And yeah, if not, I would have a question here, and that is, again, I think also Marc raised the topic at the end, and that is about validation. Is there any attempt or effort to validate your ensemble approach using, say, historic trends and maybe historic forecasting efforts and historic responses to extreme events? Is there any analog from the history that you could use to validate your approach for future assessments?
Actually, as this part of the whole assessment would be the biophysical one, the validation part is focused on the crop models. So all crop models are calibrated and validated with independent data from field experiments. But and also some of the models are considering some extreme events. But in this point, I think that most of them are a lot of room for improvement. Right. And so that this is a reason to use response surfaces, because you can move along different temperature and precipitation changes and represent some extreme environment. But I think it's something that we need a lot of modeling work yet, and experimental work too.
Yes, experimental work too. Yes, thanks a lot. Let's move to the final presentation before the coffee break, which is from Reimund Schwarze, modeling cost benefit of adaptation. Reimund, are you ready to present? I will, we wait whether he will get himself connected to our meeting, and we have 10 minutes left before the coffee break, and I really would propose to use this for a plenary discussion on the topics that we discussed in the previous 3 talks. And so there was in the chat, there was already some discussion responding to Jeroen's question on evaluating the effectivity of adaptation, if I may summarize the chat message properly. And that I propose to have as a topic for this 10-minute discussion. How can we actually sort of verify that what we are planning or projecting or mapping or modeling or visualizing is actually going to work? For Margarita's topic, that probably relies to how risky is it to make a proposal for some kind of a selection of crop cultivars when extreme climate events may be able to disrupt crop harvest in specific periods in a very big domain? Is that a risk when you use these optimization approaches? But for the other two, say, multi-criteria talks, the verification discussion comes down to, can we be sure that this mapping of preferences is leading to the right to an approach that is getting support for the broader community. And I'd like to start with the last one. So is there any work done on evaluation or say benchmarking or proving the adaptation proposals or the plans with local communities, local policymakers? Can anybody say something about the results of implementation of adaptation plans from the case studies that we have seen? Marc, I see your hands up.
Yeah, I can maybe, let's say, shortly report on an idea in a project which we will start probably quite soon. So I think one key is like if you test new medical treatments. So you simply need to create a database of knowledge of cases which are similar to yours. And for example, we are now working with GIZ on a kind of standard impact chain approach in the field of agriculture. And there we have a partner, CCAF, which have a huge database of really applied, field-tested agricultural adaptation projects. And so it's simply to create this base of knowledge from that, so that every hypothesis you have that, for example, to which extent irrigation can decrease the drought risk, to have field-proved experience from that in a structured way. So I think that's currently one way to go. So to collect simply huge databases with cases where, I mean, first on the risk side already, where a risk was really observed in the field, and also on the adaptation side, where adaptation options have been implied and then have been either successful or not. So I think that would be definitely a way to have a big database.
Yeah. But what if conditions change? Is that past database still representative for your evaluation? Maybe Carlo and then Jeroen. Can you unmute? Yeah.
I can say simply that we have to think at how much our proposed solutions are really innovative. You know? If they are dramatically innovative, of course, the risk is very high of proposing something that may fail in the future. In general, our adaptation options are well grounded in management approaches that to some extent have been already implemented. So in that case, I think it's crucial. What is crucial is how we can set a bridge between the past and the future. So how much we can, in fact, take advantage of our knowledge of the past in order to make projections into the future. This is, I think, an important element. And of course, something extremely important is to design adaptation option. We will have a presentation about adaptation pathway in the afternoon, if I'm not mistaken. So this idea of the pathway is another crucial one. So keeping the opportunity to revise the adaptation options in the future, depending on the context. Also, when we make projection about the climate, we go ahead at least 30 years to see some signals. But in between, from now to the 30 years to come, we have a huge effects from a socioeconomic context that we have to take into consideration. So I think the adaptation of the process is very, very important also.
Yes, thank you. But okay, too ambitious and innovation is more risky, which also could be interpreted then what you actually propose is something you should have already known. But that's maybe too septic. But first, Jeroen, what is your take on this?
I mean, innovation has a risk, which is evident. So we may face a situation in which we must be innovative, or we must abandon everything we did in the past. In that situation, of course, the risk is higher, and our capabilities to foresee the future should be very good.
Yeah. Jeroen? Oh, I have to unmute you. Okay.
Yeah, no,
Okay,
thank you very much. By the way, great to see everybody, and that we have an opportunity to discuss these kind of content-wise type of stuff. No, great presentations all. So my question is more like, it's good to see that these two realms of the climate change adaptation and the disaster risk reduction communities come together. I think it's really necessary, because I think the climate change adaptation is more strong into, let's say, following the policy cycle, as was also sketched out by Carlo, whereas perhaps, let's say, the disaster risk community is perhaps a little bit stronger in structuralizing the quantitative modeling approach. But I'm also quite curious about my question in the chat, which is, if you look back on your cases, so when did you really had a good feeling about, proposing this conceptual framework and presenting, let's say, all these results, perhaps a probabilistic approach or ensemble type of approaches to policymakers, and when did you have an impact? So when indeed has this led to, let's say, an implementation of adaptation? And what my experience also is to more the governance and political aspect. And obviously, I'm not a political scientist at all, but I've noticed that mapping out, let's say, the government's and institutional aspects of the arena where you're in is also quite important. And so you can have a conceptual framework, but also understanding, what are the sensitivities, and also what is the governance of all the stakeholders involved is also quite important. And this is not yet captured by this framework, I think.
This may be pretty different from a Spanish case study from Tajikistan, I would say. But maybe, Margarita, can you share some experience?
Well, actually, when I have presented this, the response has been very different from politicians than from farmers. Farmers are quite enthusiastic and ask us to reduce simulation in other locations and crops and varieties. They are generating a lot of ideas, while politicians say, oh, this is not feasible to do for everywhere. Well, I think it's not true. They're mistaken, in my opinion. But it's true that the approach is not possible to be the same for trees, that maladaptation is very, very dangerous because it's a long-term decision, while for field crops you can react from one year to another. But what we have shown here is that in modeling, not all the agreements are the same. So there is a risk in modeling. So my job is to provide the highest quality information I can for this multi-criteria approach, because the basement of this multi-criteria approach and decision tools have to be solid, are robust as Carlo defined it.
But there's more. I think there's more to it than robust information. But so, Marc, can you share some of your finest moments in your?
Yeah, maybe an exact answer to Jeroen. So I think so. I had a good feeling. Often more in a local context than in a national context, and particular when people, let's say, so when we identified a real problem which exists already today, which is quite complex, and the solution was also complex and involved more than one group of people. For example, if it's on water management, you need farmers, water managers, and so on. I think this was the good moment. The bad moment is maybe more on the national scale, and usually when stakeholders are a little bit reluctant and not encouraged enough to accept even a little bit fuzzy or maybe not super robust evaluation. So for example, in Germany, really practically, we never managed to get really to the statement, is this now a high or a moderate or low risk? Because there were so many concerns if the model results are reliable and so on. So I would say you also need a little bit of courage to come up with statements which are not fully scientifically proved by model and data. So I think that's important. And because otherwise, if you only rely on models, we will not get an answer what to do.
I think that is a very nice closing statement on a workshop dedicated to adaptation modeling, a concept that you had to get used to. But indeed, it is good to treat these models as supportive to the decision taking and not as, say, leading to the final result. There's no such thing that a model will be treated as a button to just push and then the adaptation strategy is lined out. There has to be, say, individual courage and windows of opportunity that all have to be applicable when this is done. But of course, as Margarita points out, as long as there's a lot of debate about the quality of the underlying material, then it's going to be very difficult to make a mature decision or a discussion around it. But this is, I think, a good food for thought during the coffee break, for which it is time now. If Reimund is still connected, then yeah, and if you can hear me, I do really apologize for not being able to have you run your presentation. I hope we can solve out the issue. Thank you very much for your participation. Thank you for the 3 very good presenters, and have a good coffee break. And the second part of this session will reconvene at 11:30.
Okay. Good afternoon. Good morning, I must say, obviously, to all participants to this second session on adaptation policy and planning. Welcome, everybody. We have in the coming hour 4 speakers, and let me see if everybody is available. Tim Carter, yes, I see you, so you are there. That's great to have you here. Welcome. Then Maria Mañez Costa. Hello, Maria. Good to see you again. Then we have Robert Wilby.
Yes, I'm here. Thank you.
Okay, great to have you, Robert. And we have Enrica de Chian. I hope I pronounced that correctly. She is not yet here. Okay. So what I will do is the following. We normally have with 4 speakers 12 minutes of presentation and then 3 minutes of clarifying questions. If I see that Enrica is not entering the Zoom conference, then I will try to expand the discussion a little bit more. In a previous session, we also had one speaker that did not show up, maybe because of technical reasons. And therefore, we also lengthened the discussion at the end a little bit. There are always questions to be discussed. So welcome again. 1 hour of hopefully nice presentation and discussions. So let us quickly go to the first speaker, who is Timothy Carter. Will present a presentation on a model-based response surface approach for evaluating climate risk and adaptation urgency. Tim, the floor is yours.
Thank you very much, Chair. And just to note that this will be a joint presentation with Stefan Bronzek, so I hope he can be unmuted at the relevant time. This presentation will be is about a model-based response surface approach. Margarita Ruiz-Ramos already in the earlier session before coffee introduced this impact response surface method. We are going to present some sort of applications of it for evaluating climate change risks and adaptation urgency. So the next slide. Thank you. Within the context of this meeting, of course, we're all noting that national risk assessment procedures are being followed in many countries in Europe and Europe as a whole now. This report from the Environment Agency from 2018 just shows the sort of status of different countries in their sort of progress with risk assessment, climate change impact and vulnerability assessment types of procedures. Within these risk assessments, there are a number of methods and tools being deployed. We've heard about some of the types already this morning, but it's interesting that the survey that was conducted by the Environment Agency, around half of the countries who were surveyed reported that they'd actually used modelling approaches as part of their assessment, alongside other sort of literature review, stakeholder workshop, indicator assessments and so on. So around half up to now using modelling or actually coordinating modelling approaches. And in a sense, that's what we're advocating that might be adopted, certainly in the Finnish case. By modelling, I guess we're really referring to impact modelling in a sort of classic sense. And there are a number of types of impact models that we might think of that can be deployed. for studying impacts of climate change, ranging from statistical types of models towards process-based biophysical models, increasingly nowadays behavioral models, trying to capture human behavior and decisions, but also, of course, economic models for valuation and so on. And also notable to mention integrated assessment modeling approaches, particularly at regional level. But it's an interesting point to question. These are many of them are being deployed and used for looking at impacts of climate change, but how effectively do they actually capture and simulate adaptation processes? And I've been involved in a little bit of work, a study recently to look into a review of a number of impact models in the sort of land resource type sectors, agriculture, water resources, and so on. And this review revealed some interesting sort of characteristics of many of the models that are being used in IAV type assessments nowadays. And I think one general conclusion was that the treatment of adaptation on the whole was fairly weak and cursory. So it opens a question. I think this question was raised in the first session this morning as well, about how well we're actually able to capture adaptation in our modelling. And in this paper, we suggested sort of 16 possible sort of avenues for improving the simulation of adaptation. I'm not going to go through all of these. You can read them for yourselves. But in the context of our response surface approach that we'll be talking about, we've thought that at least 4 of these would be certainly very relevant. That one should be embracing scenario uncertainty rather than looking for sort of most likely types of scenarios. That we should be working with stakeholders and decision makers to make sure that our work is relevant and legitimate. We should be including adaptation not only to hazards and negative risks, but also thinking about positive impacts as well. Certainly that's the case in Finland, that we should be looking at those. And of course, we should be considering adaptation alongside mitigation in any sort of integrated climate policy framework. We also note, and I think this point was made again this morning, that any indicators that we use and we're within our sort of modelling framework should be indicators that are relevant and could also be monitored over time, so that we can actually start to think about evaluating the implementation of adaptation as well. So now I'm going to pass over to Stefan, who will then sort of give a rundown of the impact response surface approach.
All right, so hello also from me. My name is Stefan Fronzek. And the approach, using response surface for risk assessment is consisting of applying impact models in climate-sensitive sectors with which we can then simulate impacts, but also look at different adaptation options. And these are then being used to construct what we term impact response surfaces, which have also been referred to as being conducting a scenario neutral analysis. So on what you can see on the figure on the right is a couple of examples of that from an ensemble of prop models, and they show you the model behavior over a very, very wide range of temperature and precipitation conditions, or climate conditions, if one would use other climate indicators for that. And then to play through one example, if one is able to combine these with probabilistic projections of climate change, we can actually get to a risk assessment, and that's what we want to show now. So this is an example from a crop model exercise in Finland. This shows an impact response surface for barley yield, the sensitivity to temperature and precipitation change as different contour lines. The arrow points to the baseline result of that model, and this is reflecting different conditions of atmospheric CO2 levels. So this is for an RCP 4.5 on the left, and for a higher forcing RCP 8.5 on the right. And if you move over time towards the end of the 21st century, you can see the response surface shifting and moving and changing. And this response surfaces can be combined with projections of climate change. We are using a resampled set based on CMAP5 projections. quite many dots representing individual climate projections, and we're interpreting these as a probabilistic projection of climate change, shown as the different gray cloud. Again, for different forcing scenarios, this can be shown, and if you move towards the end of the 21st century, you can see that we are reaching towards warmer and, in Finland, wetter conditions for crop production. And both of those impact response surface and the climate cloud can be overlaid. And by identifying the critical threshold, which in this case we define to be 6 tons of 6 tons per hectare as the critical yield threshold, we can estimate the likelihood of falling below that threshold. So the likelihood of a yield shortfall, which you can then see on the graph below, the estimate for the first time period. And again, if you move over time, you can see the evolving risk and evolving likelihood of a yield shortfall for these two different forcing scenarios. And then if we then add adaptation measures that can be simulated with our models, we can add to these not only the kind of the line in black, which had shown in the previous example, that would be without adaptation, but we could estimate a similar likelihood time series also with adaptation, shown in the blue lines in these two hypothetical examples. And we are intending to do this at the regional scale across Finland. One more example that is maybe also illustrative for a bit drier conditions. This is an example about irrigation demand in an agricultural area in the south of Portugal. This shows a series of different response surfaces that we have constructed that represent the inflow into a small reservoir area in south of Portugal. And the second one shows the irrigation demand from the current dominant rice cultivation in the area. And the bottom response surfaces shows the combination of those expressed as the water exploitation index, so with a higher value indicating that there is more water stress, and lower values indicating that there's enough water. And by identifying a critical threshold of the water exploitation index, one can estimate the maximum area that can be irrigated. So if the future projections show a decrease in runoff or a decrease in precipitation, then also the area that can be irrigated with that amount of water needs to be smaller also. And playing through is the same steps of analysis. We can estimate on the top row the response surfaces combined with probabilistic projections of climate change. In the second row, the translated estimate of a probabilistic impact distribution, and in the bottom row, the estimate of a risk in the first case of a decrease in inflow, the second of increasing the water exploitation index of 0.5, and the third one, the risk of a decrease in the area that can be irrigated with the amount of water available. And again, we can play this through the different time periods to see the evolving risk over time. And this is for the high forcing scenario, RCP 8.5. We can do the same for a lower forcing scenario, RCP 4.5. And you can see that the lines are shifting a bit. So the blue lines are indicating a smaller risk of not having enough water, but actually the irrigation area, the risk that the irrigation area needs to be decreased remains extremely high, also under the RCP 4.5. If we then add simulations of different adaptation options, which would be by switching from the rice cultivation that have a high water demand to other cultivations that with a smaller water demand, we can then also see that in the green lines that the areas that can be irrigated can be much larger in this case. So adaptation would be the solution in this case study. And with that, I give back to Tim for the final words in the conclusions.
So I think we're able to at least give some indication that this approach is somewhat novel and allows us to apply response services, allows us to look at sensitivity of potentially different sectors using a consistent scenario neutral type of approach. But it can also, when combined with probabilistic climate information, allows us also to look at the risk of approaching or exceeding critical thresholds of impact. And that can tell us something about the urgency, relative urgency for adaptation. And we can also then, where models allow us to do this, can also look at responses or adaptation responses and their potential effectiveness at ameliorating climate change, negative impacts, and also in relation to mitigation responses through different scenarios. We've also, clearly there are so many challenges of applying such approaches. First of all, it's very important that the actual modelling we're doing is relevant and credible, and so we need to have very, very strong stakeholder engagement in the process. We also, of course, as I've mentioned, and we've studied earlier, we need to be, I think, exploring the capabilities of impact models, in particular their representation of adaptation, how effectively are they doing this, and what sort of refinements do we need to make to those models. And there are key issues relating to how we identify critical thresholds for key impact indicators, what those indicators might be, and also the effective representation of uncertainty. But as we mentioned earlier, we're just starting a new project, started this month, and we're testing the approach in 5 sectors in Finland, and so it'll be interesting to see how what sort of results we can get with the models that we're able to work with. And with that, I thank you very much, and I'll be very interested to.
Okay. Okay, thank you very much, Tim and Stefan. Very interesting presentation, and also a strong case of showing how impact models can be embedded, let's say, in this whole adaptation planning process. We have time for a very short question. Anyone? Marc, go ahead.
Marc, you're still muted.
Can you hear me now? Yeah.
Yes.
So about the critical threshold. So because from our experience, we always had problems when we tried to do something similar to get these critical thresholds from stakeholder. And so how do you define them, or how difficult do you think they can be defined in, let's say, different sectors?
That's still an open question, I guess, because we haven't really explored this yet. We have stakeholder teams being set up, and we'll be discussing in different sectors. I think some of the thresholds may be more straightforward. For example, forest fire, we'll be looking into forest fire, and I think there are some established types of threshold for ignition and some of the sort of physical thresholds. But certainly for things like agriculture and crop yield, I mean, lower crop yields aren't necessarily an indication of lack of viability economically. It depends on the circumstances, the year, the price of grain, and various other factors. So of course we do need to have stakeholder interaction, but as you say, until we actually have that interaction, it's difficult to know how easy it will be to actually fix some of these thresholds. So it's an open question, I think.
Okay, thank you very much. We move on to the next speaker, which is I think Maria. Yes, Maria Manjas Costa. And I also see that Enrica also has joined the Zoom. Welcome, Enrica. So Maria, the floor is yours. Go ahead.
Yeah. So I'm going to switch off my camera because I have. I'm afraid that it will not work.
Yeah.
Okay. So I hope everyone can see the screen and you can hear me properly. Yes,
all fine.
Very good. So, okay, so I'm going to present you something a little bit different from the previous things. I have the feeling we were looking at how far we need proper weather and climate services to support these risk-sharing mechanisms for the agricultural sector. It's a theoretical example for a drought-prone area. And it's a work together done with Dimitri Kowalewski and myself. Part of this work was done during the IMPREX project, but we are further developing this. The background for our studies was actually the last report of 2019 of the IPCC, in which they said that for the agricultural sector in developing countries, the losses will go from 3% under 1.5 degree scenarios to 7% under 2 degree scenarios. This might sound for many people, it's only a slight difference, but for people that base their living and subsistence agriculture, it's quite a lot. So actually, what people do or are doing already with this kind of information is one, they stop investing in the agricultural sector, they change jobs, they migrate. This is what we have been looking at in the last couple of decades in migrations from Latin America to North America or from Africa to Europe. Or they start investing in putting in place crop and livestock insurances as a way of sharing the risk that they might be facing because of climate change. Of course, there are many other reactions that people might have with this kind of information, but we wanted to look at the second reaction, so risk sharing mechanisms, crop insurances, and look how it looks like actually in the world. If you look at the world in general, the agricultural insurance is subsidized in many countries, and we have expenditures of over 20 billion each year. But when you look at the total premium collected, you realize that most of this is in high income countries. So almost 90% goes to high income countries, and the rest and low income countries is only 0.03%. So we could say that this kind of insurances remains still something for rich countries and not for countries that are more dependent on the agricultural sector than the rich countries. So if we look then at the numbers, it's very interesting to see that from this developing countries list, and these are data from 2016, most of the people insured were, you could find them in China, and this is also because the government subsidized these kind of insurances as well. Only a few share were in Africa and in Latin America, but most of them actually in Asia, belonging to India and China. So despite these impressive numbers, actually the market penetration is still very, very small. And even in rich countries, it's small, it's only 3.9%. And in most of the cases, it's because the insurances are expensive and unaffordable, and especially, of course, in low income countries. But still, we have the situation that the FAO reported that 700 million are going hungry to bed, and most of these people are in these agricultural dependent countries, in low income countries. And if we want to do something to support the Sustainable Development Goal 2 and reduce or try to reduce hunger as much as possible, we need to start thinking about which kind of mechanisms could actually could start functioning that will support this risk that the agricultural sector is facing mostly in developing countries. So a possibility, as I said before, is this kind of crop insurances, and we wanted to see how far these insurances are used and why they are used and why they are not used, etc. So this kind of weather-based index insurances are actually schemes where the payouts are based on weather index objectively determined for the specific agricultural region, and therefore the individual losses assessment are not necessary. So, and this is the difference. So usually individual loss assessment is very costly. In the case of these kind of insurances, you don't need that. So they are designed not for the individual risk, but more for the climate risk that might influence regions' resilience. Our question was actually, well, they are using indices to calculate the insurances. So how important is actually a good prediction or projection to determine the use of this kind of insurances, and could we do something to increase this? So we propose a modeling approach. We develop a stochastic model to simulate the demand for insurance policies in a drought-prone area using a diversity of scenarios. And the model that we present, or the model that we implemented, actually is based on a diversity of variables. The weather index that we use aggregates actually, and also in general, the weather information within a vegetation period. This might be, in some cases, a rather simple index, which is used just only on precipitation, or a more complex one that can be dependent on, for example, daily air temperature, so thermal units, or growing degree days. In a real-world application, actually, these indexes are based on a region and crop-specific variable. We argue with our model that the strategies of individual producers in a region which is prone to agricultural droughts regarding the use of this kind of insurances and the income might be substantially influenced by the availability and quality of weather index forecasts for the region. So we show it with our theoretical model of certain dynamical features of the index projections, and we focus on modeling the strategies of producers in a drought-prone region regarding the purchase of the policies. And we also simulate the dynamics of aggregated demand for this kind of insurances, and also the strategies of individual producers. So the dynamics of the weather index for doing that, what you see in the green line is the actual weather index as they are now, defined by a particular equation. If you're interested in all of these equations, I can also send you the article that we submitted. And we do this as an uncorrelated random process with a uniform distribution. Its upper bound, the upper bound, I don't know if you see my mouse, but the upper bound is the maximum one, and the lower bound, it's the red one. The forecasted index is the blue line, and is related to the actual weather index through a statistical model with a constant systemic error and an uncorrelated random error. And the critical level actually is the brown line that you see in the middle. So the dynamics of individual producers that are shown in this figure, the brown line is showing the people that are going to be always insured, independently of the kind of forecast that you present. Then we have the green line. This is the hypothetical perfect forecast as shown in the previous picture. And then you have the imperfect forecast, which is what we have in most of the cases nowadays. So producers support in their decision-making by the hypothetical perfect forecast would benefit from the perfectly efficient adverse selection. This makes the dynamics of producers' incomes under a perfect forecast scenario quite different from the imperfect forecast case, where the forecast quality is low and therefore then the probability of a wrong decision is actually high. And from the ones that are always insurance, where by assumption, the producers will buy always the insurance in good years and in bad years. We also model the number of insured people, and of course, if you have a perfect forecast, the number of people insured will increase. which will mean also that in the face of a high risk in the future, the farmers will be able to get some additional income based on the insurance that they have bought in advance.
2 minutes, Maria.
Sorry?
2 minutes.
Yes, yes. And so I'm already by the conclusions. So the analysis that we performed suggested that the quality of the forecast would affect the optimal strategies to be selected by an insurance policy buyer under conditions of inevitable uncertainty. By generalizing this kind of proposed modeling to the case of a non-stationary random process, it will be possible to consider also whether indices with statistically significant trends that will be also important for taking into consideration climate change effects on the long term, so not only focusing on forecasts. And this will also likely shift the prospect for this kind of applications to not only the year-by-year decisions, but more long-term decisions at the climate scale. And we believe that developing this kind of comprehensive models is very important and will also facilitate the use and the acceptance of this kind of insurances. I mean, these kind of insurances are not the panacea, of course, but they might support to reach the Sustainable Development Goal 2 in a small share portion. And at the end of the day, what we wanted to look at is we wanted to look at the need for weather and climate services in developing countries. And with our results, we can say that this is actually a big call to enhance those services and to support the increase of this kind of insurances for poor countries. So thanks for your attention. And as I said, part of the finance, it came from the IMPREX project.
Okay, thank you very much, Maria, for this interesting presentation. Again, there is time for one question. Who can I give the floor? Maybe then I have a question for you, Maria. So is it true that one of the suggestions that you make here is that by offering an index-based insurance, that you also get more people insured than you would do by offering commercial insurance for that matter?
Yes, exactly. Because then the individual cost will be lower than in the other cases.
Yeah, but what I don't understand then, as an additional question, is this then a mandatory system in the sense that, I mean, people are not obliged to get an insurance policy, but they simply get money when the index surpasses a certain threshold, right?
Yes, right.
Yeah, but actually this is also a little bit already happening because I mean, Red Cross and other NGOs are also already experimenting with cash transfers, right?
Yes.
And this is basically a sort of formalization of cash transfers. Is that correct?
Well, something similar. Yeah, it will be small and on individual basis because the individual farmer will decide if they want to have insurance or not. Mm-hmm. In the case of the cash transfers, it's most like a region. So the region has a flood and then money flows in this direction.
Right, right.
It will be a regional direct sharing mechanism.
Yeah. All right. Well, thank you very much for this interesting presentation. We quickly have to move on to the next speaker, which is Robert Wilby from Loughborough University. We know each other only, I think, from being on the same paper, Robert. Yeah. But nice to see you now almost live.
Yeah.
The floor is yours. Go ahead.
Okay, I'm going to have to switch my video off as well, because I live in a small English village with terrible internet. So okay. I apologize. Okay, sure. So I'll turn that off. Let's share my screen. Okay. Okay, can you see my screen?
Yes, perfect.
Okay, great. Well, thank you very much for the invitation to participate in this Europe-wide workshop. I'm very glad to be part of the discussion. And it seems that Tajikistan, although a small country, is figuring quite prominently in this breakout group. What we're looking at here is an image of the Karakum hydropower plant in Tajikistan, which has undergone about a $200 million refurbishment over the last several years. And of course, adaptation globally now is a really big business. We're looking at least $15 billion of investment last year alone, with that figure set to rise considerably as we go into the future. So what hangs over all of these discussions, I think, is are these adaptations going to deliver intended benefits? And I think that kind of question has already been asked. And Tim introduced a range of measures that people have been thinking about to address that question. I'm going to cover just two this morning. So how can we be confident that these huge investments are going to deliver the intended benefits? Well, in my simple worldview, we've got three options. We can wait and see for a few decades to see whether the hydropower plant delivers the electricity we were hoping to get. We can use models, and we've heard a lot about that this morning. Or there's an area which I think may have been overlooked. We can use field trials and experiments to test very specific adaptation interventions. And I'm going to give an example of those two main streams of approach from my own work. But before I do that, I want to just sort of, again, I think acknowledge, as other speakers have done already, that we are having to adapt to climate variability and change in the context of other huge mega trends that are occurring alongside and with climate change. So we're seeing, particularly in Western Europe, demographic change. We're seeing globally a move to more urbanized populations. We're seeing rapid growth of new technologies, resource stress, and on the right-hand side, you can see that we're also having to think very carefully about trade-offs between sectors, like how do we meet future water, food, and energy needs whilst also adapting to climate change. So I think right at outset, we need to adopt this very much an integrated approach. We can't really do justice to adaptation thinking without acknowledging that the adaptation is occurring within this much broader socioeconomic and environmental context. So I think that's a key point I'd like to make at outset. I think others have already shown really nicely how concentrating on the hopes and fears and goals of the decision maker from outset is a key step forward. So often in the past, we've begun with the climate model information and pushed that onto the decision maker. I think now there is a genuine understanding that we need to start with a collaborative dialogue. And this circular graphic was how I essentially captured what was essentially a 2-year discussion with Denver Water when we were thinking about how to help them adapt their water supply system. And I emphasized this notion that it was a two-year cyclical process. It was iterative, and it was much longer than I'd anticipated for all the parties involved to arrive at a shared understanding of not only what are we trying to achieve, but how do we measure success. So I think, again, other speakers have already highlighted the importance of agreeing meaningful performance metrics. And here in the case of Denver Water, they want to have a water supply system that is reliable, meets the competing water needs of lots of different water users, manages residual risks, protects the environment, and so forth. And within this framework, models appear on the sort of right-hand side in terms of the system evaluation. So we're essentially creating a virtual world using the model. And within this virtual world, we are using to test different management options under different narratives or storylines of change. And again, I'm using those words very carefully, storyline or narrative, because it's a much richer way of thinking about the future than just saying we're going to look at this through a climate change lens alone. We need a more comprehensive narrative of how the river basin as a whole might change, how the land cover might change, how the climate changes, how other elements of the system, both physical and managed, might change in the future. And we sort of demonstrated this approach, as I said, for the upper Colorado River Basin, which supplies the water needs of Denver and vast swathes of the Colorado Front Range. And our virtual world was captured within the water evaluation and planning model. And this enables us to simulate both the physical system and also the licensing system, which is incredibly complex. All the rules of who gets the water first, who gets what's left over, how much do you give to the environment. This is in some ways more complex to represent than the actual physical system, but it has to be in there alongside other credible drivers of change, such as how might forest cover change. If we imagine a hotter, drier future, we want an internally consistent change in the land cover, so perhaps more forest dieback. We might, if we're envisaging a hotter, drier future, imagine more dust on snow events, leading to earlier melt of the snowpack. So again, I'm emphasizing this idea that we need this holistic view of the catchment response with and without the adaptation. And when we put that those narratives into the model, alongside an adaptation, in this case, the adaptation was one measure in which an upstream water license holder essentially gives away their rights to take the water first and gave it to Denver Water under certain drought conditions. And we evaluated the extent to which this gives more water in storage, which is what the water company wanted to know, under control, which is essentially the present situation, and under three narratives of change, which were essentially a warmer future, a hotter, drier, dusty future, and a future which is hotter and drier, but also has loss of vegetation. And we represented that change in vegetation within the hydrological model parameters. So again, it is all internally consistent. And what emerged from this analysis was quite modest changes in storage, up to 4% in an individual year. Here we've got the effect of the adaptation relative to no adaptation over a 30-year period. And that was actually less than the water company were thinking they might get from this adaptation. But nonetheless, it's enough to meet the water needs of 300,000 citizens. So it's still a non-trivial adaptation outcome, and certainly worth considering. So that's my first example, using the modeling environment as a virtual world to explore narratives of change with and without adaptation. Now I turn to perhaps an area which has received perhaps less attention, which is designing bespoke physical experiments to test adaptations in the field. And in the UK, and as with across Europe as a whole, there are concerns that water temperatures are rising and that this has a big impact on the ecology and the health of the river. So what can we do to essentially buy time for these fragile ecosystems and threatened species in the face of relentless increases in water temperature? And one of the simplest suggestions that has been widely put forward is to plant more trees along the edge of the river, particularly in the headwaters, to create more shade, to reduce the radiative loading on the water body, and essentially cause cooling. And you can see that across England and Wales, the top map shows all the points in the water sampling network shown in red where temperatures have been rising, and this is in the vast majority of sites. So what we did nearly 10 years ago was set up this field experiment to undertake very high resolution monitoring of water temperature in space and time under different types of riparian vegetation. So sites with lots of shade, sites that were open, sites that were affected by weirs and so forth. And we ran this experiment monitoring the temperature changes in relation to air temperature at the same site. So we're beginning to pick up a picture of how the variations in riparian shade might impact water temperature under different circumstances. And here we bring in the modeling as well to combine with the field experiment to say, what if we plant trees in this part of the catchment, recognizing that the landscape itself also gives us a lot of shade too. And what we can see on the left-hand side is a downstream annual radiation entering the river system as a measure of the heat input. And the black line shows the energy receipt for a treeless landscape. So you can see that there are parts of the headwaters where there's much less energy receipt because there's deep shade from the landscape, and likewise further downstream. And it's in the middle reaches where we see the highest levels of solar radiation. And when we plant imaginary trees into this landscape, we can see the reduction in the energy shown in the green line. And this is the benefit being offered by the adaptation. We're making the rather optimistic assumption that our trees are going to grow 30 meters high and will grow quicker than the pace of climate change. That's another discussion in itself, but I just want to acknowledge that. Anyway,
Rob, 2 minutes, by the way.
Okay, yeah, thank you. Anyway, through this analysis, we can show that basically, if you plant a kilometer of riparian shade, you get essentially a 1 degree reduction of cooling at the monitoring sites downstream. And what we're saying here is that this is exactly the kind of simple rule of thumb that practitioners want. Just tell me a simple rule. How many trees do I need to plant to achieve a given degree change in the water temperature? And I think as a community as a whole, we should be striving to collapse all of our complex modeling into these simple, what we call rules of thumb. 1 kilometer of shade gives me 1 degree of cooling. So just to close then, what more do we need? I think we need more scenario generators, tools that can stochastically create credible narratives of change, which include both the climate and the wider changes in the catchment in this case. In this situation, we have to be quite clear about what we regard as plausible ranges of change. You know, is 6 degrees a big enough change to really stress test the system, or do we push the envelope even further out? The second thing I think we need is workable guidance for practitioners, as I hinted at before, where we take our sophisticated modeling and analyses and stakeholder engagement and just collapse that down into workable guidelines for engineers and decision makers. And this is something that I've been trying to do for the Asian Development Bank, shown here in the middle. And finally, I think we also need to develop workflows and tools that are super low tech. And I think there's a lot we can deliver through the humble Excel spreadsheet, which step by step guides a decision maker through these sorts of analytical procedures we've been discussing this morning. So at that point, I'd like to close. Thank you.
Thank you very much for this interesting and excellent presentation, advocating simplicity and transparency, I think. Very relevant. So let me quickly see if there's one question that we can take up here. Anyone? If not, Rob, can you maybe then expound a little bit on this rule of thumb? Is this a little bit of a similar recommendation as others gave with respect to defining thresholds, or is it different?
I think they're different ideas, but they're complementary. So in my understanding, the threshold is identifying those conditions, both climate and non-climatic, that stress the system to a breaking point. So at what point does your water supply system fail to deliver what you need to meet the needs of society, or at what point does your yield fall to a level where the farm revenues become too low to meet costs? And that's quite distinct from what is the efficacy, the effectiveness of a given intervention to a given amount of climate change. So if we, going back to the tree planting example, if we fear a 4-degree future, then that implies in this particular river basin, you would need to plant 4 kilometers of continuous riparian shade to protect that river from 4 degrees of warming in the summer. So I think they're complementary ideas rather than in competition.
Sure. Okay, well, thank you very much for this answer. We quickly go to the last speaker, which is Enrica de Chian. I hope I pronounced your name correctly.
Yes.
Please go ahead, the floor is yours.
Good morning, and first of all, thank you for the invitation, and I think for me it's a great opportunity to be here. So as you might know, this was like a last-minute change to the program of this workshop, this session, but I think, okay, this presentation actually fits very well with the discussion that has been going on, especially because it somehow further developed one of the points that was raised by Timothy at the beginning regarding the need to consider adaptation alongside mitigation in an integrated framework. And what I will be presenting is a research effort that we are undertaking within a ERC project, which is precisely trying to do that with a specific focus on energy. I mean, energy has been studied a lot within the context of economic growth, mitigation scenarios, and most of the attention has been on the loop, the relationship that goes from energy to climate change. But instead, a bit less attention has been paid to what I call the climate energy feedback loop. That is how changes in climatic condition will induce new needs for energy use. I mean, it should be clear that, of course, there is a huge literature in the economic sphere addressing energy demand in relation to climate condition, as well as other important variables. But this feedback relationship is actually missing in most integrated assessment modeling, in most effort. I mean, even if you consider most of the scenarios that are being used to study decarbonization transition pathways, this second arrow, this second relationship is often missing. And this is what we are trying to do within this project. This is important. You might be aware of the report that was published by the International Energy Agency in 2018 on the future of cooling, highlighting the importance of the cooling sector. I mean, maybe it's a bit of a jump. Cooling is the typical example of how we use energy to adapt to climate change. And already today, energy for cooling is accounting for almost 10% of the global final energy. So it's a sector which is growing at a scaring speed, also because there are still many homes, especially in emerging economies such as India, that still don't have air conditioning. Plus, there are many new buildings which are being built, especially in emerging economies where we are observing very rapid rates of urbanization. And the issue is, let's say, of concern not only in emerging economies, but also in some of the more developed and colder countries, because even countries such as Spain, which is, okay, a warm country, but even France, the Netherlands, Sweden, these are colder countries, but those are places which are not used to operate air conditioner, but where climate conditions are increasing the need for this type of energy service. Here you see just an example of indicator variable. Those are the imports of AC, so the value of imports across different OECD countries. And you can see that the imports of AC have been increasing quite significantly in countries that traditionally have had low air conditioning penetration, such as Spain, France, and I was pointing before at Netherlands, Sweden, and even Switzerland. The point is that there is still quite significant potential for further increase, because if we look at the electricity consumption for air conditioning as a share of final residential electricity, I mean, in many countries around the world, European countries, emerging economies, we are still quite low, and we are expecting growing trends. In this graph, you see the US on top, setting the upper bound, and Europe setting the lower bound. And within, you have emerging economies where we are expecting the fastest increase. But even in Europe, we are seeing a growing trend. So starting from this background, first of all, we look into integrated assessment models. So we have conducted a review on global integrated assessment models, which should appear in ERL soon. And we have identified only 14 studies that actually include the climate energy feedback, so that explicitly model the energy needs for adaptation with the specific reference to the cooling need, space cooling need. We did also a quantitative comparison of the results. I mean, there is quite a wide range of variation, but there is robust evidence of regarding the increasing needs for cooling, which are highlighted in red. The box plot highlights variation across models as well as across SSPs. There is a robust, let's say, agreement regarding the reduction in the need for heating. And the two together, I mean, these two changes put together lead to a change in the net final energy demand that can be positive or negative, but we observed in most cases at the global level to be positive, meaning that the cooling needs would prevail. So results are pretty robust, but still the wider implication of these trends on the economy as well as on the energy systems are not well understood. And in addition, the modeling of air conditioning penetration and of the use of air conditioning among agents and households within models is still pretty stylized. So in this project, we are trying to improve these. We are trying to study what are the main factors that determine the decision to adopt AC across different countries, because as of today, most of the evidence that we have is for the United States, but United States might not have the same behavior as families in India, Mexico, or Brazil. So we're trying to characterize households' behavior with respect to this decision And we're trying to understand what are the implications in terms of electricity expenditure and electricity use for households, as well as at the more aggregate level, and with the ultimate goal of looking at the system-wide.
2 minutes, Enrica.
Sure, system-wide implications. Just to give you a couple of results with respect to the analysis of the determinants of two important decisions connected to thermal comfort of families. We look at air conditioning and thermal insulation as possible options. And we have examined a number of variables. So climate measured by CDDs, income are important variables. Urbanization also plays an important role. And it seems that families living in cities are less inclined to better insulate their houses, whereas it might be easier to simply install an air conditioning unit. Also, demographic variables such as age, gender play a role, and attitudinal characteristics such as, meaning if a family is more oriented toward energy saving behavior, this is also influences their decisions. We have also compared these behaviors in OECD countries with emerging economies. This is a work that we have in progress. And basically the bottom line is that the main drivers are common across the two group of countries, but the magnitude of the effect is quite different. For example, whereas in, let's say, rich country, climate plays a bigger role, of course, in emerging economies, which most of them are actually located in a hot climate, their income plays a more important role. I think another very interesting, then we're using these empirical results in order to develop scenarios of adaptation with the specific of AC adoption and use. And here I'm showing you the change in AC adoption across 4 emerging economies we have analyzed. And you see in blue the historical pattern across income decile, so from poor 1, 2, 3 decile to rich people 9/10 decile, and the red is a future projection for one SSP RCP combination. So you see a huge increase within rich households and middle income households, but a big gap still remaining within the poorest one.
We have to wrap up, Enrica.
Yeah. So yeah, I'll leave it to the discussions. Here are some points of discussion, so I'm hoping to receive your questions, and maybe I can add starting from your question. Thank you.
Thank you very much for this also very interesting talk. One quick question is possible. Anyone? Clarifying question?
Could I ask a question? Sorry, I can't raise my hands. Rob again.
Sure.
Yeah, fascinating study. Thank you for that. I suggest there might be another blind spot out there, and that is that as worldwide dependency on air conditioning grows, we're also locking in a high degree of vulnerability to the loss of that air conditioning. So if there's an extreme event or an outage that causes catastrophic failure of the energy supply system, then we are suddenly exposing potentially millions of people to extreme temperatures with all the terrible ramifications of that. So perhaps there's actually 2 blind spots here.
A quick answer, quick response, Enrica?
Oops, sorry. Yes, I fully agree. And we saw some example of that during the lockdown in hot countries where there were actually, especially in the US, power outages, leaving households more vulnerable. And yes, for sure, we need a transformative change in order to reduce our dependability on AC.
Okay, I think these are great words actually to end this session. I have to quickly go to the plenary. I hope you can join there to make a sort of summary of this quite rich set of presentations. Thank you very much for making your time available, and I do hope that I can see you real life in the near future. Thank you very much.
Goodbye. Thank you.
Thank you. Bye-bye.